Hello students, welcome to your first astronomy lab. Today's lab will guide you through angular size and it'll give you a good reference point for a lot of the other things we talk about in both the lab and the class. So this is the first lab. You'll find the exercises, whether you're in class, they'll be on the astronomy laboratory software. And if you're at home, you'll be watching these videos and going through with me reading the example problems for you. So today's lab deals with how we actually measure things in our sky and compare that to the real size of these objects. So what is angular size? It is how much of a given view an object occupies. So the simple example is the sun and moon. Looking at our sky, they occupy a very small part of the sky, just a few degrees is what we would say. And to put that in terms that you can measure, if you hold your thumb out, that's about 2 degrees, hold it out at arm's length, and that's about as big as the sun and the moon appear in the sky, no matter where they are in the sky. So if you hear people talk about how the moon looks bigger when it's low in the sky, you can put your thumb out, give a thumbs up symbol as far out as your arm will go, and measure the moon. It'll be about your thumb size, and when it's high in the sky, it'll be about the same size. So again, a thumb is about 2 degrees if you hold it at arm's length, and if you measured that all the way from one horizon, measuring upwards till you get straight above you, that would be about 90 degrees, so it would be about 45 thumbs from the horizon to straight above you. And then you could go all the way to the other horizon and get the full 180 degrees at 90 thumbs approximately. And your pinky can also be used. Your pinky is about 1 degree. So we break up the sky into 180 degrees from one horizon directly above you to the other horizon. We can also break up the cardinal direction, so north, south, east, and west, into 360 degrees, so you can make a complete circle if you're measuring from one direction to another. And using this, we can actually measure how wide things are in degrees or radians or arc seconds or minutes. So radians just break up into decimals, so 2 pi radians is a complete circle, and then as you go down from that, you just get decimals. 360 degrees is a complete circle, and you can break each degree up into 60 minutes, and then each minute can be further broken up into 60 arc seconds. So similar to how hours are broken up into minutes and seconds, that's how degrees are, except there's 360 degrees in a circle. And in today's lab, we're mostly going to be using arc seconds, but we will need to convert to radians to actually make the mathematics work. So angular size's use is to measure the apparent size of things, since we can't go up to these celestial bodies and measure them directly. So even the moon is fairly close, but it would be a lot of work to send a crew to the moon to measure the distance from one side to another and then try to figure out from that distance the diameter of the moon, or the distance from one side of the moon to another as we're viewing it from Earth. And this also brings up the point that far-off objects appear much smaller. So it makes sense to us that as objects get further away, they look smaller and smaller until eventually they disappear. Many things in astronomy are visible to us, but they're so far away that they look like just pinpoints of light. So the moon and the sun are super close, relatively speaking, compared to the stars and even the planets, most of the planets. So they look bigger, and some of the planets actually do look like they take up angular size in our sky, so you can kind of see a circle when you look at a few of the planets. But pretty much everything else in the sky looks like a pinpoint of light because it's so far away. And as you'll learn in the class, most of the stars we can see in our sky are very, very big, much larger than our sun. So since they're so far away, they look much, much smaller. The example here is this crab is viewing these two objects. These two objects are the same size, but since the green object is so much further away, the crab sees that object as taking up much less of the sky. So if that crab were to measure the angular diameters of those two objects from one side to the other, alpha would be the angular diameter of the blue object, and beta would be the angular diameter of the green object, alpha would appear much bigger, a much bigger number to that crab than beta would. So we could say that the angular size or the diameter or even the radius is the angle swept out from one side to another. So the diameter would be the full object from the left side to the right side to our viewer, and the radius would be measuring from the middle to the edge. And in today's lab, you're mostly going to use the diameter from one side to the other side, but we will talk about the radius a little bit. Again, just getting the math to work. And then if we want to make any sense of these measurements, we need to know one more thing. So we need to know the distance to the object. So if we know two of these three things, we can figure out the other one. So we might also know how wide the object is, and we could use that in the measured angle to figure out how far away the object is. Or as we'll be doing in today's lab, use the known distance to the object to find the diameter. All right, so moving on to the calculations we'll be doing for this lab. We are set up with a situation like this where we or a crab is viewing an object, in this case a planet, from some distance away, and the first thing they measure is the swept out diameter. So from one side to the other they find some angle, and that angle we are going to call alpha. The distance from the observer to the planet will be given. And just to make the mathematics possible, we are going to use trigonometry to figure out the diameter of the planet from the angle found and that distance. So first we've broken up into the radius. What that does is allows us to form a right triangle, which we need for any trigonometry using right triangles. So this is the right angle here, and what we have is the adjacent side. We're looking for the opposite side, and we have this angle here, this a/2, so it's half of the original swept out angle. And you might be wondering, why is this distance measured to the center? Maybe you think we should measure to the front because that's how most distances to objects are measured. But the thing is, in space, most things are so far away that the actual size of the object is very, very small compared to how far that object is away. So imagine something is 1 billion kilometers away from us, and it might have a width from the front to the back of 10,000 kilometers. So the difference between here would be 1 billion measuring from the middle. 1 billion minus 10,000 would get us here, and 1 billion plus 10,000 would get us here. And the difference between those two numbers is very, very small. So there's a lot of empty zeros between the 1 in 1 billion and the 1 in 10,000. So in astronomy, a lot of times we just brush over these and imagine that they are similar numbers, and that's what we'll be doing today. So measuring to the middle of these planets, but it's very close in the grand scheme of things to the front or the back. So now that we have these numbers, we can bring in our trig function. So tangent of our half angle of this angle here should equal r over d, or the opposite over adjacent. And then we can do something known as the small angle approximation, and what that allows us to do is approximate this function here, tangent of this angle, as just this angle. So a, or alpha over 2, is equal to the radius over the distance. And we can do that with angles that are sufficiently small. So you might be wondering what sufficiently small is. A good rule of thumb is less than 1 degree. Definitely everything we'll be doing today will have angles less than 1 degree. You might run into trouble if you start measuring things like the moon or things that are even bigger in the sky than the moon and trying to use the small angle approximation. So the moon, you could probably do this. It's about 2 degrees. You may even be able to measure things slightly bigger, but if you get above 5 degrees, I definitely wouldn't use the small angle approximation. So again, that small angle approximation allows us to basically get rid of the trig function completely and just be working with the number. So what we're left with here is the angular size is approximately equal to the diameter of the planet over the distance. And that happened because, again, we don't want the radius, we want the diameter. diameter is just radius times 2, but we can't just multiply one side by 2. So we multiplied both sides of the equation by 2. That got rid of this half angle that we needed for our trig functions, and that also gave us the diameter instead of the radius. And then rearranging that equation, we get equation 1 in the handout. The actual size or diameter of the planet is equal to its angular size times its distance from the observer. But I did leave one thing out. This angular size is in radians. Just to make the math work, it needs to be in radians. And radians are sometimes hard to measure in the real world. So you can say that 180 degrees or a half circle is pi radians, and that a full circle is 2 pi radians. But other than that, measuring radians, or making actual measurements in radians is what I should say, is quite hard to do out in the real world. That brings us to our next set of equations, basically going from measurements that are easy to make into radians so that we can calculate our actual sizes of planets. So the first thing we want to do is convert degrees to radians. Most people tend to think in degrees, so that's where we'll start. Basically, if you have an angle in degrees, multiply that by 2 pi divided by 360, and that will give you that same angle in radians. However, the measurements we'll be making in the lab today are in arc seconds. 1 arc second is 1/3600th of a degree. So we will also need to convert that to radians to actually get us somewhere where we can make these calculations. So equation 2 down here is where we will need to start most of our calculations for this class, or for today's lab. So we have our distance in kilometers. This will be given in the lab. We multiply that by our measured angle in arc seconds, and then first we'll multiply that by 2 pi over 360. That converts from degrees to radians, and then we want to make sure that we are also in degrees, so we convert from arc seconds to degrees using the 1/3600 here. So if you know the distance in kilometers and your angle in arc seconds, you can now find your actual size. You could also rearrange this equation. If you knew the actual size of an object and you knew its angle in arc seconds, you could figure out its distance from you in kilometers as well. So equation 1 and equation 2 should be what you need for today's lab, especially equation 2 will be the equation you'll be using most of the time. So now we will work with an example just to make sure that we have the idea of how to work with the numbers. We're talking about a balloon here, but it works exactly the same as the planets will work in today's lab. So you're viewing a spherical balloon as it floats away, and use an extremely good protractor and rangefinder to see if its diameter will change with altitude. After some time, the balloon is 4.2 kilometers away from you, and it appears extremely small in the sky. And then you measure the left side of the balloon. It is at 0.015 arc seconds from the center, and the right side of the balloon is negative 0.015 arc seconds from the center. What is the balloon's diameter? So the first thing we need to do is find the angular diameter, or just the diameter of the balloon as it appears in the sky. So not everything we'll work with will be perfectly spherical, so measuring from the center could be hard. But what you want to do is take the positive number, subtract the negative number, and you should get a positive number. So this angular diameter is 0.03 arc seconds. From this, we can plug into equation 2, so we know the distance to the balloon, we know the angular diameter of the balloon, and we plug it into this equation here to get the diameter of the balloon in kilometers. And once we do that, we find that the diameter of the balloon is 6.1 times 10 to the negative 6th kilometers, and that is 6.1 millimeters. So this is a very small balloon. You would need very, very accurate tools to actually keep track of it at that distance, but this size in arc seconds is quite similar to what you would be looking at if you're looking at a far-off planet, or maybe even one of the moons of that planet. So imagine a 6 millimeter balloon at 4 kilometers distance. That's somewhere around I don't know, 2 or 3 miles. That is the size of many of the things that we think are quite close to us and easy to observe in our astronomy class. So keep that in mind for many of the things we'll be talking about, both in the lab and in the class.